So far, everything we've studied has been about electric fields created by static charges. Coulomb's law, Gauss's law, electric potential, all of that was electrostatics. Now we enter a brand new chapter, magnetostatics. Here, the source is not a stationary charge, but a steady current. And the first question is, what magnetic field does a current produce? The answer is the Biot-Savart law. Consider a thin wire carrying a steady current I. Take a tiny piece of this wire, we call it dl. This small element creates a magnetic field dH at some point P, located a distance r away. Biot and Savart discovered that dH equals I dl cross a hat r, divided by 4 pi r squared. Let's break this apart. The magnitude is proportional to the current I and the element length dl. It falls off as 1 over r squared, just like Coulomb's law. And the direction comes from the cross product. dH is perpendicular to both the current element and the line from the element to point P. The direction of H follows the right-hand rule. Point your right thumb along the current. Your fingers curl around the wire, and that curl direction is the direction of H. For a current going into the page, H circulates clockwise. For a current coming out of the page, it goes counterclockwise. We mark these with a cross for into the page and a dot for out of the page. Biot-Savart works for any current distribution, not just thin wires. For a line current, we integrate IDL along the path. For a surface current with density k amperes per meter, we integrate kds over the surface. For a volume current with density J amperes per square meter, we integrate JdV over the volume. The link between them is simple. IDL equals KDS equals JdV. Now let's apply Biot-Savart to the most common case, a straight wire carrying current I. Place the conductor along the z-axis and pick a point P at a perpendicular distance ρ from the wire. The wire extends between two endpoints. We define alpha 1 as the angle at the lower end and alpha 2 at the upper end, both measured from the wire axis. After integrating the Biot-Savart law along the wire, we get H equals I over 4 pi ρ times the quantity cosine alpha 2 minus cosine alpha 1. The direction is along a hat phi, circling the wire. This single formula covers every straight conductor problem. Two special cases come up constantly. First, a semi-infinite wire, one end at the origin extending to infinity along Z. Here, alpha 1 is 90 degrees and alpha 2 is 0, so the formula gives H equals I over 4 pi ρ. Second, and most important, an infinite wire stretching from minus infinity to plus infinity. Now alpha 1 is 180 degrees and alpha 2 is 0. The cosines give us 1 minus negative 1, which is 2. So H equals I over 2 pi ρ. This is probably the single most important result in magnetostatics. To wrap up, the Biot-Savart law tells us the magnetic field from any current distribution. For straight conductors, it boils down to a formula with two angles, and for an infinite wire, the result simplifies to I over 2 pi ρ. In the next video, we'll apply these formulas to solve example problems step by step.